Yeah, thank you so much for the introduction. I hope the voice will be fine, but otherwise just let me know if you can't hear anything. But I think this will be good. Otherwise, just interrupt me in the middle of anything, really about anything, and we'll just see where we get. Yeah, today I want to talk about AutoML applications and language model post-training. So I'm really personally much more an AutoML user. I have no idea how the algorithm works, and I'm going to tell you that it still works for me, and how we use it, and how this helped us in inference optimization. So the first topic I'm going to talk about here is going to be about model merging. So I might be talking about this paper with my great student Guinan, who is not here today, who's on vacation. But this is actually the paper, and this is the code that's also online. And I'm going to be presenting mostly also work that I've done with her, also mostly also her work here in this presentation. So what is model merging? If you've never seen this might be a bit surprising. So let's start somewhere else first. You've probably all seen a lot of model fine-tuning, right? So you have a base model, maybe like this llama, all the way on the left, right? And you can fine-tune this base model to have different capabilities at deployment time. Maybe you want it to have an armor, maybe you want it to, maybe you want to train it a bit more safer, or you want to train for the sword. Maybe this will be here an analogy to a different capability, right? And so you can do all these fine-tunes for all these different capabilities and all these ways you might want to use this base model. But then how do you combine them, right? Maybe the standard way is that you then try to do another fine-tune. You try to put these data sets together, and you just pile on more data sets. You try to stop forgetting things to eventually get this model that, for example, here has both the armor and the sword. And this is maybe like the traditional way of doing this like post-training adaptation of models for different domains. But what's interesting is that a different way of approaching this is the idea of model merging. So here we still have our original base model. It's still a llama on the left. And what we do is we fine-tune these different versions of it, like before. But now what we can do is, because these are both instances of the same base model, they can actually be merged together, which in the simplest way means just to average the weights of both models. And this sounds kind of wacky if you haven't heard about these before, right? Because these are 13 billion parameter models, and the easiest way to merge them is just to average both of their weight vectors into a new weight vector. And surprisingly, these often still work. And these are models that then can use capabilities from both of these fine-tunes. And this is kind of interesting because it does something slightly different than just fine-tuning it on more data, because you sort of make these two fine-tunes, so you accentuate different performances in both models, and then you merge them back together. Although actually, if I say that it's just an average, that's maybe a bit of a lie, because actually there's a whole literature on how you could make this merge slightly more optimally. For example, you can do something like task vectors, which I'm describing here, where you basically compute the difference of the fine-tuned model to the base model. These are also vectors, and then you can do some calculus on these vectors and how you put them together. And you can quickly imagine that there's a lot of hyperparameters involved in how you merge things, and it's very easy to think that you want to get the llama on the left, but you set up the merge parameters in the wrong way, and suddenly the model has forgotten how to speak English or something, right? Because ultimately the merge is pretty much a black box where you do this intervention that's pretty cheap, right? The merging itself of the two models is very cheap, but you might not know what you're getting when you do the merge. And to like illustrate this a bit, I brought this slide. So what's interesting is that merging is a bit unpredictable. So on the left here, what you see is some reasonable default merging parameters. And here I'm always merging two models. For, the first model all the way on the left is just the M is just the math model here. This is a math fine-tune of this llama model. And I can actually merge that model with the code model, which comes next. So math and code performance is great on this benchmark here, right? This is the second chart. But now I say, oh, that sounds cool. Maybe I can also merge it with the instruct model, which is a different fine-tune, right? So I merge math and instruct, same formula, performance is disastrous, right? Or I merge with code and instruct, also disastrous. Well, no, code and instruct is here, or I put all three together. Suddenly it works again. This chart is only to tell you that, like, by using default parameters for this merge, it's a bit unpredictable how well it works. And even if you think you have a good combination of model pairs, something like this like math model and the code model, which, by the way, in this talk we'll often merge this math model and the code model because we kind of want a model that's useful general purpose, but has better math capabilities. And the math model is good at math, but it's also a bit over-tuned on math, and it really loves answering questions and benchmarks. And you kind of want this capability to come also into actual deployment and into actual chat with the model. So that's why we'll often try to merge this math model into a base or into a language model. Language here meaning a chat model, instruction model. But so even if we merge just math and code, like on B, with different merging configurations, performance can vary wildly. And then you might think in this room, yeah, this looks like an AutoML problem, right? There's hyperparameters for how we set up the merge, and so we kind of want to search for a good set of hyperparameters, so this merge goes well, and we actually reliably get a better model out. Pretty straightforward. But the interesting question is, like, how do we set up this whole search space? And in this paper, I'm going to talk about two interesting ones. But it's definitely not an exhaustive list, and this is kind of what we've looked at in this paper and what we found interesting. So one thing that you can do, which we have on the top, is you can do this layer-wise fusion, which is kind of like exactly what you would expect, is you have your list of candidate models, and then your search space is the hyperparameters for how you merge these models for every parameter in the model. And this is a very large search space because you now have a hyperparameter, or you have, if you have, for example, you have 5 different ways to merge a model. Each of these 5 ways might have like at least 5 hyperparameters for how the merge works. So now you have 25 hyperparameters, and now you have them per parameter in the model, or parameter group. This blows up very quickly. So what we do here often is we make these larger groups. So for example, the first 4 layers get the same merging parameters, and then the next 4 layers get different merging parameters, and this way we can group it and reduce the search space size. Yes. Yes. Yeah.
What's the disadvantage of, for example, setting up 2 LoRa layers and then training them in parallel or something like this, such that they can effectively feed each other? Then I merge them directly, and I still want to find that properly.
I mean, if you merge your 2 LoRa's together, you're doing model merging.
But like this is done after training.
Yeah.
And if I like theoretically could merge them during training already, right?
Yes.
So why? What's the advantage of doing it after training?
It often behaves differently, which is a very practical statement, or like there's not a lot of like why and how behind it. I don't think it's something we have like understood well yet, but it's often something where, for example, what often ends up happening is that the fine-tune is a more extreme version of this behavior. So the fine-tune is really good at math or really good at chat, and afterwards, after we've made these fine-tunes, or we've made a fine-tune of math and chat data, we kind of want to dial it back a bit. We want to have a bit, maybe the model should be a bit less chatty, but a bit more mathy. And this like dialing around, we can often do later. Sure. But maybe there's also like another point is also that people often look at this also from an efficiency angle, where they are given these different fine-tunes from different organizations, and they want to adapt to their own setup without having the data that these other companies had. But that's maybe a bit more of a industrial setting that's not so often so interesting. Yeah, but so like you kind of want to dial these things around and find like the optimal spot. Where just like to one final example for this is like, for example, if you've used many of the recent deployed like chat models or like Gemma models, these are often models trained in such a way that you do the safety tuning, for example, of the model. So you get a very safe model. And after you've done that, you merge it back with your starting point to like dial it back a bit to how exactly where you want it. Yeah, and then so like here, what we're going to talk about next is so we have these search spaces. And then the answer question will be like, right, this will just be data driven. We don't need to like look at the model and eyeball how good it will be. We'll just have some set of data where we want the model to have a particular behavior. And we're going to run our AutoML procedure to get this behavior on that data. Yes. The theta here is more of a shorthand for all the parameters that you would have in this merge. For example, like there's like different operations like here and like for example task arithmetic. There is like a theta parameter how far you move in direction of this vector. If you go back to my picture here of task arithmetic, you can sort of like add these two task vectors together, and then the hyperparameter is like how far do you move in that direction. But for something like some slurp is like an interpolation on a sphere, there's different hyperparameters for how the sphere interpolation is working. So it's really, in this picture, just a shorthand for all of these, kind of. So the top part is what I just talked about, which is sort of like averaging in this layer by layer or parameter by parameter. We take a parameter group, we look at the same parameter group from these different fine tunes, and we merge them together. But interestingly, language models are very malleable. So what's a bit more wild is you can also do the thing on the bottom. The bottom is depth-wise integration, which is interesting. So here what we're doing here is we collect all the layers from all the fine tunes that we want to merge together, but now we don't merge them together on a parameter by parameter level, but we build a deeper model made up of all the layers of these different models. So we decide to say, okay, we're going to take layer 4 from the first model, and then we're going to take layer 5 from the second model, and layer 5 from the third model, and then we take layer 6 from the first model, and so on and so forth. We build like a new model by combining layers and then putting them into one after the other. And we might even like repeat layers multiple times. And usually in language models, these operations all kind of work. And so this is a different way to construct here in the bottom a larger model, but a model where we didn't merge parameters together, but we just played Lego with the model. Right, so, but of course for both of these, the big question is like how large is the search space? Can we actually find something efficiently? So there will be lots of grouping here, right? So one thing I haven't talked about yet is we can also make component groups. So even if we have the same merge parameters for the first 8 layers, we might still have like 3 sets where we have one set for the layer norms in the model and one set for the attention weights and one set for the feed-forward weights. So we have these component groups. All in all, we collect a search space, and a bit similarly for the depth-wise version, right? If you think about this as Lego, and then you can imagine the search space pretty much immediately, right? You just have all these possible combinations, and so then you can search over that. Although actually this depth search is a larger search space then. And then what's the objective? Here, of course, what's pretty nice is that we're doing AutoML. This is a zero-order problem. We have a set of validation benchmarks that we want to be good on. So we search for model merging parameters that we want to be good on these benchmarks. But what's of course important here is that, so after we've searched on these validation benchmarks, of course we can't really eval on them anymore. These ones are done. But we can then look at holdout benchmarks and see how good we are there. What's also kind of important here is that this way we get a pretty direct feedback from the model, right? This is not a proxy for how good the model performs. We literally, right, maybe the benchmark might be like math tasks. So we actually merge the model together in some way. We generate 100, 200, 500 answers for these math tasks, and we really check if the answers are correct. Right? So it's not a proxy, it's the actual task that we're trying to solve. We want this model to be good at, for example, at chat, but we want it to still be solving these math tasks correctly, right? And so we generate text, and we see whether it does it, and that's our evaluation loop in the objective. And then, of course, you can also imagine that we can do this with multi-objectives, and we can find a parameter frontier over many things we might want to have, and then trade off on that frontier. Right, but ultimately, this is still a bit expensive, right? Because these models are so large, there might be ways we can overfit with our merging, where if we only have, let's say, like 5 questions we're always testing, we'll get those 5 questions right eventually with some wacky merge, right? But actually, we need a larger validation set of queries that we're testing because the model has a very varied behavior, and we can't just eval it with just a few questions. So a lot of the efficiency of the search is in doing something like multi-fidelity, right? Where we don't want to search all our database of 10,000 queries, because if we see after 10 or 20 that the model's merge was really bad, then we want to stop. But if we think the model merge is a good candidate, right, then we keep on pushing more and more compute into the evaluation to be more accurate on our objective. And the solver, actually, this is a very simple slide. In this project, actually, we just use SMAC. And we actually really minimally changed the settings, I have to say. And it's not even, and it's an interesting question of like whether it's actually is a good idea to use it here. But I think it's surprising that it works anyway. So what comes out of this? Lots of tables like this, which look kind of wacky, so I'm going to move to this slide. Right, so what we find is models where there's kind of a representation of what's happening in this weight merge. But what we find is that we really do merge these different models together. So the optimal model that we have here, for example, for a math benchmark, is one where we actually don't just use the math model, which is in purple, but in multiple layers, we do merge the code model in it. And then in the third block of layers, we actually also merge the original language model, the code model, and the math model. And this way, this really is a merge of the model. And then if we look at benchmarks, this is a bit of a long slide, so I'm going to point out a few fun things on it. So what's interesting is that if we just look at math performance on a single task, then what we really can do here is that, or maybe I should not move so far away. It's interesting that we can improve performance on this math benchmark, because this model is already fine, like here, this math checkpoint, which you see in the first row, is already fine-tuned to be good on math. This is actually what it's actually trained on GSM 8K, right? It's not so clear that we would be able to merge in other parts of the code model, for example, and of the language model, and improve on math performance. But interestingly, we actually do improve. We improve on, we see it in the bottom, we actually find 4% more math performance for this, even though like sort of on top of this math model. And then we trade this off, right? But of course, like what you see on the slide here is also that this is a bit of a trade-off, right? For example, we trade off better grade school math, and we lose a bit on this other math benchmark, which is math. So this is more algebra. So this is often a trade-off, but we can play around here, and then we can find the model that we want to our specifications. And this also works if we look for multi-objective optimization. So here, this is pretty much just the Pareto frontier are these like models 0 to 5 here on the bottom, 0 to 4, which are different parts of this Pareto frontier with different flavors of how much do you want common knowledge, how much do you want math, how much do you want coding. And then we can trade off and figure out which model we want in the end. Yes?
Because like, are these models all the same size in the end, or can this ones with the layers have more layers?
So here, this is all this first search space, which is just this weight merging. So these are all the same size. These ones, here you see two more in the bottom. These ones actually are a bit larger. Not actually 4 times the size, because that would be too expensive, but we make them about like 20 to 30% larger. And interestingly, this also works. You can also actually improve math performance by doing that. If you slot back here. But interestingly, this depth-wise merge, while it's possible, is not as powerful as the weight merge, which is something we found here. But it's still pretty interesting, because with the depth merge, which doesn't work as reliably, you find models that look a bit like this, where you start out with the original language model, and then you use the first layer from the math model, and then you go a bit further, and then you use the 12th layer and the 15th layer from the code model, and then you, at some point, for example, here you use this layer, and then use the same layer again, but from the code model. So you repeat the same layer, right? And ultimately you build this model, which is then a bit larger than before. And language models really are malleable like this, which is kind of surprising. So base here means it's the uninstruction tuned model. So it's like the base pre-trained model versus, so yeah, LM, and then here is the chat model. So like the language ability model.
I think in the previous slide you had
Yeah.
So that's this basic one, right?
Yeah.
So that's just merging the summing of the layers and releasing normal levels.
So basic here is if you only have permitted tune for one merge method, then this is how much you get out. So maybe what I've also been saying, like, you can also just, of course, use the same framework in a bit more straightforward way of you pick one merge method, maybe you pick ties merging, and you run the same procedure to have permitted tune ties merging, and then you get these 3 out, right? The first one, you optimize only the parameters for ties merging. Second one only for task argumentary, and third one for linear. These are different merge schemes. And this is optimizing only for those merge schemes. And for example, on average, this is a pretty good gain, but you can get a bit more by sort of like tuning which method to use on which layer group. that help?
I just wonder, like, if you were to train on the video with data sets,
Mm-hmm.
that would be,
Mm-hmm.
and would that be much also like, how do you compare?
It's a bit hard to compare. It's pretty hard to for example, it's pretty hard to train on GSM at K and then improve further. And we can sort of like, we can throw all these into one pot and then just train on it. And it doesn't do that much, but this doesn't mean that there is not a good way to train with this big pot and then have it be good in evaluation on all these. But it's not so straightforward. For example, also like several of these models are then trained with different settings on their own data sets, and it's not so clear what settings to use when putting them in a big pile together. I don't have a good answer for that. Like, I think it is like on a theoretical level feasible that there is a good sort of like mix of this data that would have the same performance. I think that seems like it should be there, but I'm not sure what the weight of the data sets would be and how to train it necessarily. But I would think that there is such a mix.
Which ones do you actually merge together all in the same family? Or
yeah, so this is right, like really, it's really, if you go, really important to go all the way back to this, the first slide, right? You start out with this one base llama model, and you make fine tunes of this model. So these are really from the same family. They kind of, you have to use a more fun merge method. Because basically, if you think about it, even if you train the same model twice from different initializations, you have these rotations and these permutations of the weights where the actual order of the weights is under-specified. So you first need to search for permutation matrices to like fit these different checkpoints back together. And that's a much harder task. So here, by starting from the same checkpoint, you know that the weights are in the same order and they kind of mean similar things, although the models drift from each other, but they don't drift radically.
do you find them directly on the weight, or do you add something? Like you have a more available?
These two here, this is like Mammoth and then Math Coder. These are full fine tunes. Yeah. These are like 3 state-of-the-art fine tunes. This is like a state-of-the-art math fine tune for this model, and then a state-of-the-art code fine tune that we also didn't train, by the way. Like we also didn't train these fine tunes.
So here you're merging like math and another task, math and code together. But do you think that, I don't know, let's take Llama 3 that was not understanding German very well. So that we take Llama 3, we feed more German.
Yeah.
We fine tune on German language, and then we fine tune on original lemma on a task specific topic. Would that make sense to merge them together or not?
Yeah, so we have this, I didn't bring this slide actually. We also tried this with Japanese and math, for example, and this works very well. There's another nice paper from this, from Martin at ETH. But basically, it's interesting if you fine tune first on math and then on the language, you end up forgetting the math a bit. And if you fine tune first on the language, you forget the other one around. And by merging, you can get around this forgetting problem. So it's a bit advantageous actually to do, especially this this kind of merging, if you want to get different languages to have these capabilities. They have a paper on doing this for Bulgarian actually, where they end up making different fine tunes and then merging them back together to give a model that's both knowing math and Bulgarian.
Is the library using also for decoders, or that's for software encoders, or just for decoders?
Our code is pretty much for decoder models. You could probably adapt it, like ultimately, right? Like how the model is being evaluated is pretty much a black box to the search, right? In the way that the model is, there's some function that evaluates the model on the data set, and an accuracy comes out. So that's pretty much encapsulated. So you could probably encapsulate a different model architecture in there. Yeah, but now on the, how much time do I actually have left? Well, I'm actually on time, right? So the last topic is actually what we've already talked about briefly, which is like if you think about this like as like Lego, right? Then it's very clear that you can't just make the model deeper, but you can also make it shallower, right? So you just run the same search to prune a model. What's pruning? If you haven't heard about this, so pruning is the idea that you pre-train a model, it has a particular size, let's say it's 7 billion parameters, 32 billion parameters, whatever you have it. But then maybe like your inference time requirements change somehow. You want a smaller model because it fits onto a different device somehow, or you want to do something else with it, right? And you don't really want to pre-train another model with like 5 billion parameters. So you'd want to prune the original model to your new size requirements. And how do you do that? And there's lots of ways to do this. Of course, there's also lots of research into unstructured pruning, where you try to remove parameters all over the model. But what's very nice for inference efficiency is you do something like structured pruning, where you can use hardware acceleration in a good way. And in this talk, it kind of makes sense, right? You've seen that we like merge layers together and like play around with layers. So here, what we'll just do layer-wise pruning by just turning our entire like machinery just towards pruning, right? So we run the same algorithm. We again have multiple base models, and then we sort of like use the layers from those models that do the task particularly well, and if the layer does none of the tasks particularly well, it goes out. So it's the exact same thing I've told you before for merging, right? But now we merge and then we prune in the same step, which is just, of course, a binary vector of like, do you keep this layer or not, which we just add to our search space. And this is interesting that it works because the fine-tunes almost accentuate some of the performances. Like the fine-tune is like better at math than the normal model. And then if we take some layers from math layers from this math fine-tune, this is better than just pruning the original base model, which we could have also done, right? So we just set a pruning ratio, maybe like 25%, and then we just run our search. And then interestingly, we get something like this, where right, again, we put these models together, and we find that maybe we start with some layers from the language model, then we feed in here, the second layer is then a merge of language, math, and code, and it goes and so forth. Here's the language and code model, then a few layers only from the code model. And here, what you also see is that we save layers, especially at the end of the model. And we're also not the first people to discover this. There's also a bunch of research on this, that like often the model is a bit, like in the later layers, it's doing things that are a bit more subtle or in domains that we don't care so much about. So those layers are a bit more higher on the chance to be removed. And then taking it all together, it's again a big table. I'm going to skip over it very briefly. That like it works pretty well to merge these models together. And so like using the 4 base models and then merging them together gives you a better pruned model than just pruning any of the 4 of them. And you can kind of see like how if you vary the pruning ratio, how much you get out of it. And this is an average of these benchmark scores, where like, of course, you make the model smaller, it is less capable. But for example, if you between like 0 and 37% of pruning, it's a pretty nice linear decay on this chart. It's not so catastrophic. After so like 37% here, at some point, we really start to lose the model and what it's doing, and then we really fall off very drastically. But in this range of like moderate pruning, this is very successful. Yeah, so much for using AutoML for merging and pruning, right? So these are really sort of like the inference optimizations, not in the way that we're running inference faster, but in the way that we're optimizing our model for a particular inference objective goal or deployment task, right? And that's very hyperparameter dependent, and it's a very good use case for AutoML. And interestingly, also this whole thing is not so different from neural architecture search, right? We're kind of doing an architecture search, just by not training the model. We have the model already trained, but to me, it like really feels related because we're just picking these different layers from these different models. It feels a bit like picking like different where you pick a conf or an MLP from, right? It's a bit of a similar way of thinking about it, maybe. Which maybe also implies that what maybe really the question here, like how well this works, is really about how the search space is designed and how do you set this up in a way that makes sense. And yeah, here was one way of setting up these search spaces, but I'm sure there are others that might even be better. Yeah, thank you so much for your time. And I think I have some time for questions now, and let's talk about them.